we are looking at the solution for the implicit spectral method in one dimension for the diffusion equation, and the solution that I wanted to show. So, there are some parameters that are not chosen properly. So, I have now corrected that, and I am going to go through the code once more, and then we will run this code and see how the solution looks like. Okay, the first step is to clear the memory and figure. So, clear all and then clear figure, and we define the system size, which is 128. We define the diffusivity. So, let me say system size and parameters. So, the diffusivity is also defined. Then probably it is a good idea to define del t also here instead of defining it later. So, del t is defined later as 1.0. So, I am going to make it 1.0 here. I am able to take a del t of 1.0 because remember we are dealing with an implicit method. So, there is no constraint on what delta t you have to take for the calculation to be stable. Of course, smaller delta t will will make the calculation more accurate, but stability is not a problem. So, I am allowed to take a larger delta t. So, I have taken a delta t of 1, and then we make a sinusoidal profile. So, we first define the C vector, it is a column vector, and we say that there will be two waves in this domain, which is 128 domain, and the two waves, that is why m is equal to 2, and we make a sinusoidal profile. And this composition profile, so I have made a mistake here, it should be 0.5, right. It should be 0.5 times 1 plus sine. So, because sine goes from -1 to +1, if you add 1 to it, sine will go from 0 to 2, and if you multiply by 0.5, it will go from 0 to 1. So, that is the reason why this 0.5 multiplication is there. So, we have made a sinusoidal profile. Okay. Now, what we are going to do? So, we are going to plot the initial profile, and we are going to say hold on, so that the other profiles will be plotted on the same thing. Now, we need to implement periodic boundary condition. This is a spectral technique. So, we need to first define half the length of the domain, that is called half n, and then we define the delta k, because remember we are in the Fourier space, we are going to solve this equation in Fourier space. So, we do not need the delta x, we need the domain discretization in the reciprocal space. So, that is delta k. So, that we have defined, and then I have, as usual, there is a loop for plotting, there is a loop for evolving the composition, and then there is a loop for actually evolving using the implicit technique. So, for doing that, I need to take the Fourier transform. So, C tilde is first Fourier transform of C, then I go 1 to n, and this is where the actual boundary condition is implemented. Okay. So, I should probably also modify this. So, this definition of half length is for periodic boundary condition implementation. Actual periodic boundary condition implementation is being done here. So, I will say periodic BC implementation. So, that happens here, and then we say the new composition is nothing but old composition divided by 1 plus d k squared del t, and k is what is defined, and k is defined consistent with periodic boundary condition. So, that is the only trick in this code. If you do, then the new composition we know, but this new composition is in the reciprocal space. Okay. So, we evolve it for all the reciprocal space points, and we evolve it for 500 time steps, because that second end for is for the time loop 1 to 500, right. So, we have this 1 to 500, and that second loop ends there. So, this is the end for the second loop. And then when we want to plot the composition, we want to plot it in the real space. So, inverse fast Fourier transform of C tilde, that will give me the composition, and we want only the real part, because this Fourier transform and inverse Fourier transform will have both real part and imaginary part. So, we want only the real part, because I am in the real space and the composition is a real value, it is not imaginary, and it does not have any imaginary component. But numerically when you are doing, you might pick some imaginary component, that is because of errors, and we want to get rid of it. So, C is real part of inverse fast Fourier transform of C tilde. So, this C I plot, and then I end. So, this end for will make sure that I have plotted for several times. Now, the last thing, of course, you can print minus d JPG to the device JPG. I can say that implicit spectral dot JPG. Okay. So, let me save this and let us run this. So, I have to source implicit spectral 1D diffusion dot. Okay. So, again because this is sinusoidal profile, the composition evolution is expected in the same way as it was in the finite difference case, namely that wherever the curvature is positive, that region is going to increase, wherever curvature is negative, that region is going to decrease, and this system is going to go towards homogenization, and that is precisely what we see here. So, you can see a red line and you can see several lines which are basically the evolution of the composition. So, let me just take one of these parts, one wavelength, and you can see that is what it is doing. So, this is the same as we can go closer and take a look at it. So, this is basically the composition evolution as a function of time. So, it starts at red and then the composition is coming down, and in the other part the composition is going up. So, whatever extra amount of composition that is coming down here is going to go into that region and is going to bring up the composition. So, here also we see that finally the composition will become a straight line. Okay. So, this is the spectral technique, 1D diffusion equation solved using spectral technique, and like I said, as part of exercise we will do several initial profiles. Thank you.